Hello friends, welcome to SRINGERI B.Sc College YouTube channel, and today we are going to discuss in this video application of Laplace transform in a shifting theorem. In previous video we have discussed first and second shifting theorem, and we know that the shifting definition of the Laplace transform, and that is first shifting theorem. First shifting theorem is a convenient way of solving Laplace transform is of the form e to the power at f of t. Suppose there are two conditions in a first shifting theorem. First one is if Laplace transform of any function f of t is equal to f of s, then we are already familiar with the first shifting theorem. When a Laplace transform of e to the power at f of t can be written f of s minus a, and in second case of first shifting theorem is e to the power minus at f of t, and that is f of s plus a. We will see some standard examples with the help of standard tools of Laplace transform. Let us start with the one simple example. Calculate Laplace transform of e to the power minus t sin t. So this is very simple, and we have to solve this condition with the help of the Laplace first shifting theorem and some signals of the Laplace transformation. So we will see solution of Laplace transform e to the power minus at sin t. So first we have to compare with the first shifting theorem. Look at the this condition with the second condition. Just compare it. So e to the power minus at sin t, here condition of first shifting theorem of second condition is e to the power minus at. So a is any constant, so here a can be replace 1 and f of t is nothing but sin t. First we have to calculate the Laplace transform of sin t. So our f of t is here f of t is sin of t, and now we have to apply the Laplace transform on both sides, which implies Laplace transform of f of t is equal to Laplace transform of sin t. So we are already derived this one, Laplace transform of sin at. So just compare with the Laplace transform of sin at, and we get a over a square plus a square. So a is nothing but here 1 constant value. So in place of a just substitute a 1, and we get the 1 over a square plus 1 square is nothing but 1, and this is Laplace transform of sin of t. Hence Laplace transform of e to the power minus t sin t is equal to 1 over a square plus 1 with the help of the first shifting theorem, and we have to change the s value as a s minus a or s plus a, so as our convenient. So here e to the power minus is there, so s can be changed as s minus 1, because a value is s plus 1. So because here minus is there, so in solution, in answer we get in addition, so a value is 1, so s as change as s plus 1, and which implies 1 over s can be changed as s plus 1 and whole square and plus 1, and this is the solution of Laplace transform of e to the power at sin t. Get some other examples. Calculate Laplace transform of e to the power t plus 1 whole square. So very simple, just we have to compare with the shifting theorem. So e to the power t and f of t is given t plus 1 whole square. In solution part, so first we have to consider f of t as t plus 1 whole square, and we don't know the solution of this one. We have to simplify or with the help of the algebraic simplification, and this one is a plus 1 whole square formula we have to apply. T square plus 2 times t plus 1. So simplification of t plus 1 whole square is nothing but t square plus 2t plus 1, and next we have to apply Laplace transform of apply the Laplace transform to the f of t, and Laplace transform of t plus 1 whole square is equal to Laplace transform of t square plus Laplace transform of 2t and Laplace transform of 1. So now look at some standard rules or signals of the Laplace transform. So first one, and now calculate Laplace transform of t square, and we have to compare this one with the Laplace transform of t to the power n. So there are two conditions for the t to the power n. One is gamma of n plus 1 over s to the power n plus 1, or n factorial over s plus 1. So suppose the value of n is in fraction, then we have to apply the gamma function, and here n value is an integer, so better you apply n factorial over s to the power n plus 1. Now look at this condition of Laplace transform of 2 to the power n. So n value is 2, and Laplace transform of this t to the t square is nothing but, so n is 2 factorial, and yes, and n value is 2 plus 1 3 s cube, plus Laplace transform of 2t is nothing but to take outside, and Laplace transform of t is nothing but power is 1, n value is 1, so 1 factorial 1 plus 1 is square, and Laplace transform of constant value, any constant value can be written constant over s. It means the value of a is nothing but 1 over s. So by algebraic simplification, 2 factorial is 2 only, 2 over s square plus 2 and 1 factorial is 2 over not s cube, s square and 1 over s, and this is nothing but Laplace transform of t plus 1 whole square. Hence Laplace transform of, so now apply the shifting theorem. So e to the power in given condition e to the power at and t plus 1 whole square, and we calculated f of t value is 2 over s cube and plus 2 over s square 1 over s. So with the help of the first shifting theorem, and here s can be changed as s can be changed as e to the power at is there, So we have to apply first condition of shifting theorem, and that is s as constant value is 1, s changes as s minus 1. So just replace s as a s minus 1 in this condition, and that is our solution of Laplace transform of given condition. So this one is 2 over s minus 1 whole cube plus 2 factorial s minus 1 whole square plus 1 over s minus 1, and this is the solution of Laplace transform of e to the power t of t plus 1 whole square. And now look at some examples. Find the Laplace transform Find the Laplace transform of e to the power t sin t cos t. So again, with the help of the first shifting theorem, we have to calculate this one, and in solution here we have to consider as sin t cos t is our f of t. F of t is sin t cos of 2t. So if you apply the Laplace transform on both sides, and it's difficult to calculate when trigonometric functions are in product form, and we don't have the standard condition for this one or standard tool for Laplace transform. And so with the help of the trigonometric function or trigonometric compound angle formula, we have to solve, or we have to simplify this one. And we know that the trigonometric functions sin a and cos of b formula is nothing but we can write 1 over 2 and sin of a plus b plus sin of a minus b. So this is the compound angle formula, and we have to compare with this condition, and we get the solution, or in simplest form, sin t cos of 2t, a value is t and b value is 2t. So 1 over 2 sin of a plus b, a value is t and b value is 2t. So a plus b, t plus 2t is nothing but 3t, and plus sin of t and 2t, a value is t and b value is 2t. So t minus 2t is nothing but minus t, and again simplify, sin 3t, sin of minus t can be written minus of sin t. So in a simplest form, with the help of the compound angle formula, we can write 1 over 2 sin 3t minus sin t, and this is our f of t. Now we have to apply the Laplace transform on both sides. Apply Laplace transform. F of t is equal to 1 over 2 and Laplace transform of sin 3t sin t. So again simplify, 1 over Laplace transform of sin 3t and minus Laplace transform of sin t. And now we have the standard signals of the Laplace transform. We have derived already for general formula for sin at and sin of at. So just we have to take this condition, sin Laplace transform sin at, and apply the formula, that one. So a value is 3, so 1 over 2 is constant, and sin 3t, a value is 3 over a square plus 3 square and minus and a value is 1 over a square plus 1 square. So this is our Laplace transform of f of t, that is sin t and cos of 2t. Hence with the help of the shifting theorem, we have to find out the Laplace transform of e to the power t sin t cos t, Laplace transform of e to the power t sin t cos of 2t is equal to 1 over 2, 3 over a square, and 3 square nothing but 9, and 1 over a square plus 1. And now we have to change s as s minus 1, because first shifting theorem says that e to the power at is there, so which is in positive, and in frequency domain we will get in minus. So here s change as s minus 1, the value of a is 1. So in this one, 1 over 2, 3 over s minus 1 square plus 9, and 1 over s minus 1 whole square plus 1. So this is the solution for the Laplace transform e to the power t sin t and cos t. If you want further simplification and just simplify, just apply a minus b formula and whatever you get, and apply a minus a whole square formula, and by algebraic simplification, and we get solution, or stop here only, and this is the solution for the given function. So again, some more examples for Laplace transform. Find the Laplace transform of e to the power 3t sin square t. So with the help of the first shifting theorem, we have to solve e to the power 3t sin square t. And look at here, our f of t is nothing but sin square t. So if you apply the Laplace transform on both sides, then we cannot be get the easily. So we have to simplify sin square t with the help of the trigonometric formula, and that is double angle formula. And after that, after simplification, we have to apply the one of these in this condition, and definitely we get the solution. So sin square x can be written, 1 minus 2 time cos 2x over 2. So 1 minus cos 2x over 2. So this is the formula. With the help of this condition, and just simplify sin square t. So sin square t can be written 1 minus cos of 2t over 2, and this is our f of t. And now apply the Laplace transform on both sides, and definitely you get Laplace transform, one of the standard tool. So f of t, and I will take here 1 over 2 as a constant, and remaining terms are Laplace transform of 1 minus cos of 2t. Now bilinearity property, linearity property, so Laplace transform of 1 and minus Laplace transform of cos of 2t. So simplify. So Laplace transform of 1. So we know that the any constant value of Laplace transform can be written in a frequency domain 1 over, it means a over s. Here a value is 1, so we write 1 over s and minus and Laplace transform of cos of 2t. So look at here, any one of these, here we have to compare with the standard signals. So cos of at can be written s over a square plus a square. So here a value is 2, compare with this one, fourth one, cos of at, it means a is 2. So this one can be written s a square, and a value is 2 square nothing but 4. And this is our Laplace transform of sin square t. Hence with the help of the first shifting theorem, we have to calculate the given condition e to the power 3t and sin square t. So Laplace transform of sin square t, we have this condition, and now apply the first shifting theorem, and that is Laplace transform of e to the power 3t sin square t. So this, which is equal to 1 over 2 1 over s minus s square plus 4. So now we have to change s as s minus 3. So in this condition we have to change s minus 3, because e to the power at, so which is in positive, a value is 3 and s minus a is 3. So very simple simplification, 1 over 2, and that is s minus 3, and s we have to change s also, s minus 3 whole square 4, and this is the solution for given function. And try yourself, find the Laplace transform of e to the power minus t 2t. So simple, with the help of the trigonometric function, double angle formula, we have to calculate first sin square x, cos square x, and definitely cos square x value is nothing but 1 plus cos of 2x over 2. So apply this formula for this one, and so just go through the same procedure and definitely you get the solution. So in next video we have to discuss some more examples or application of Laplace transform with the help of the first and second shifting theorem. So thank you.